Okay, good morning, good afternoon, or good evening, depending on where you currently are. My name is Laurent Schmalen from Karlsruhe Institute of Technology in Karlsruhe, Germany. And in the upcoming hour, I'm going to tell you a little bit about spatially coupled LDPC codes. And I will focus on the theory, but also show one or two applications of these very interesting type of codes. So my talk is outlined as follows. I will start with a very simple introduction on channel coding and LDPC codes, and then show how you can generate spatially coupled LDPC codes from LDPC codes. And we'll see some of their properties. We'll look at the performance, at the practical implementation, and at some improvements. And in the second part of my presentation, I will show the burst correction capabilities, which are quite outstanding for this class of codes. And also I will show an application example here. So in this talk, we are focusing on channel coding. As you probably know from your communication engineering classes, channel coding is an indispensable component of every communication and storage device. And channel coding, and in particular block coding, which is a part of channel coding that we are focusing on in this presentation, encodes a vector of length k into a larger vector of length x, which has n elements. So n is larger than k. So we add redundancy. And the amount of redundancy that we add is called parity bits. So we add n minus k parity bits to our code word. And the definition, the formal definition, is that the channel encoder essentially takes these k input bits and uses them to map or to generate one out of 2 power k possible output vectors. And these output vectors, they belong to a code. And a block code essentially is nothing else as a collection of 2 power k, or as we call it, m vectors. So it's a collection that contains m vectors x1, x2, up to xm from a field. And in this lecture, we are just focusing on the binary field, so GF2. So the elements of the vectors are binary numbers, and they are of length n. That's the definition of a code. The channel encoder then does nothing else as just indexing these different vectors and assigning to an input bit pattern a certain vector from our code. So that's the block code. And we are focusing on one subclass of block codes, which are linear block codes. And we are exclusively focusing on linear block codes. Linear block codes are sufficient for achieving Shannon's capacity. So it's sufficient to look at linear block codes, and they possess some very nice and interesting properties for implementation. And a linear block code is essentially a k-dimensional linear subspace of our vector space f power n. Because we have a linear subspace, we can represent the code using a span of a basis. And this is the basis are formed by k different code words. And we group these k basis code words into a generator matrix, G, of dimension k times n. And the rows of this generator matrix form the basis vectors. So in coding theory, usually put the basis vectors in the rows and not in the columns, as you may be used to. And this has a historical reason. The definition has been like this, and that's why we keep it like this. So the code essentially is generated using this generator matrix. And the generator matrix is used and is multiplied with all possible input patterns of length k, and this will give the code words xi. Alternatively, we can see the code also as being a null space of an orthogonal matrix to the generator matrix, which is the so-called parity check matrix. It's a parity check matrix, and it's called H. G times H transpose is equal to 0. So all the elements in the parity check matrix are orthogonal to the basis vectors. And the code is then obtained as being all vectors from our vector space Fn, such that H times X transpose is equal to 0. That's the definition of the code. So here is an example. We have a parity check matrix H, and we have an example code word X equals 11100, and we can verify this is 111000. So we can just verify that this is equal to, if we multiply this row by this column, so we get 0 times 1 plus 1 times 1 plus 1 times 1 plus 0 plus 0 plus 0. So this is equal to 0. You can do the same thing for the second row with this column, and we see that we also get 0. And if we repeat this for the third, we also get 0. So we actually have verified that this vector is a code word, and we can do the same for all possible vectors, and then we get the set of our code words. So essentially, it's like finding all the solutions to a system of binary equations. We are looking at one very specific subclass of linear block codes, which are extremely popular these days, and these are linear low-density parity check codes, or LDPC codes. An LDPC code is a linear block code where the parity check matrix is sparse, which means the number of ones in H is small compared to the number of zeros. And what is the reason for doing this? Well, the reason is was mostly motivated by Gallagher in the 1960s when he invented these type of codes as a means of reducing the storage requirements. We know that a random code with a random parity check matrix can achieve capacity, but the storage requirements, even for storing this matrix, they scale as O to the n squared, which is not necessarily feasible even for medium values of n. So Gallagher wanted a way of saving the storage requirements. So he said, okay, the number of ones is going to be very small compared to the number of zeros, so I can compress the matrix very efficiently. That's the reason for introducing LDPC codes. So we're looking at, again, a very specific subclass of LDPC codes called regular LDPC codes. And the regular LDPC code, and we denote it using this tuple dv and dc, is an LDPC code where each column contains exactly dv number of ones, and each row contains exactly dc number of ones. And dv and dc are both larger or equal than 2. So we look at this parity check matrix. Each column has dv number of ones, and each row has dc number of ones. And because the number of ones is small and fixed per column and row, the memory complexity for storing this matrix is just O to the n. So let's take a look at an example. Here's an example of a code, a parity check matrix of rate 1/2 code with n equals 48, m equals 24, dv equals 3, and dc equals 6. So we can actually verify. We pick a random column, and we see there are exactly 3 ones in this random column. Pick another random column, exactly 3 ones. Exactly 3 ones. We can do the same for the rows. So we can take a look at an arbitrary row, and if I'm able to draw a straight line, then you'll see that exactly there are 6 ones in each row. And the same for any other row, and you can verify this for yourself. This is still a small code with n equals 48. So in practice, we are talking about n in the range of 10,000 to 60,000. And for this code, the density is 12.5%, but it will quickly decrease as n grows larger. When we look at these codes, the parity check matrix is not always the most convenient way of representing them. So there is a very nice isomorphism between the parity check matrix and a graph. And this graph representation or tenor graph of the code is a very nice way of visualizing. So we have the code of our parity check matrix that we see here. For this code, we see that dv is equal to 2 and dc is equal to 4. So we can verify each column has 2 ones and each row has 4 ones. And what we do is, to each column of the parity check matrix, which corresponds to 1 bit of our code word, So each column corresponds to one bit. First column corresponds to x1, second column to x2, third column to x3, fourth column to x4, and so on. We draw one of those circles, which are called variable nodes. And then what we do is we generate the graph by looking at each row of the matrix. So we're looking at the first row of the matrix, and the first row of the matrix essentially gives us an equation saying that x2 plus x3 plus x4 plus x5 must be equal to 0. So what we do is we insert one of those called constraint nodes. The constraint node corresponds to one parity check equation that must be fulfilled. In this case, the one that you see here. And we connect the variables or bits that are involved in this equation with lines to the constraint node. So we did this for the first row. We can repeat this for the second row. Then you'll see you have one of those boxes. The second equation should be equal x1 plus x3 plus x4 plus x6 being equal to 0. So you connect x1, x3, x4, and x6. That's how you generate the second constraint node. So I do this in a more beautiful way. And then you repeat the same for the third one, which is the last row of the matrix, and you'll get the tenor graph of the code. So this is the graph representation of our code, and we'll use this graph representation later. This can, of course, be done also for larger codes. So here we have a larger code, which has a dv equals 3, this equals 6, and this is the parity check matrix, and this is the corresponding graph. So you also see that the graph quickly becomes visually not very pleasing to look at, but it's still extremely useful to represent the code with this graph, also for doing the decoding. We'll not do the decoding explicitly, but we'll get to the decoding algorithms. The channel we are looking at is the binary erasure channel. And for the sake of simplicity in this presentation, we'll stick with the binary erasure channel. It's a very simple channel model that in the field of coding enables an extremely simple analysis, but it's still very close to practice. So for instance, it can be used to model packet losses in packet networks or losses of servers in distributed storage devices. Or it can model high signal to noise ratio channels, like you have, for instance, in optical communications. You can model them very well with binary erasure channels. Binary erasure channel essentially has 3 channel outputs. It has a third output symbol, which is the question mark. And the symbol is either received correctly or it's mapped to the question mark symbol, which is an erasure. So if we receive a 0 or 1, we can be sure that a 0 or 1 has been transmitted. But with probability epsilon, we receive a question mark, and we cannot infer if a 0 or 1 has been transmitted. So this is the binary erasure channel. The capacity of the binary erasure channel is extremely simple to calculate, and it's just 1 minus epsilon. So if there are no erasures, you have a capacity of 1. If every symbol is erased, you receive only question marks, and you cannot infer anything, so the capacity is equal to 0. But the capacity is exactly equal to 1 minus epsilon. Okay, so how can you analyze the behavior of the decoding? And what is the necessary epsilon on the binary erasure channel for decoding to be successful? Well, for this, we need to define what is decoding. And the predominant decoder in practice is something called an iterative message passing decoder. And this iterative message passing decoder essentially exchanges beliefs about the different bits along the edges of the graph representation. So it's also called belief propagation decoding, or BP decoding, or message passing decoding. And conceptually, it's very simple. Essentially, you look at the different edges in the graph, tell you how probable it is that a certain message has been erased or not. And we'll not look at the decoder as such, but at the analysis of the decoder. And you can actually analyze asymptotically the performance of the decoder. So you need to fulfill some asymptotic conditions, meaning the block length of your LDPC code should go to infinity. And this decoder is an iterative decoder. And you can analyze the average erasure probability during decoding by a simple update equation, asymptotically. So you have an erasure probability XCL after L decoding iterations, and it's given by this update equation. So it's epsilon 1 minus XCL minus 1 to the power of DC minus 1 power of DV minus 1. And we initialize with Xc0 being equal to 1. So initially, all the messages are erased. We know nothing about the code word, and then we will slowly recover. And we can decode successfully if this XCL goes towards 0. So if this XCL goes towards 0, decoding is possible. And now we denote the threshold of the decoder. So the threshold of the decoder is the largest epsilon for which this happens, for which XCL is going to 0. So let's take a look at an example. Here we have a code that's called the 3.6 LDPC code. So dv equals 3, dc equals 6. And we look at this erasure probability XCL as a function of the iterations. And we do this for different values of epsilon. So for epsilon equals 0.45, we see that we converge to a fixed point of 0.35 roughly, so we cannot decode. So we have to decrease epsilon a little bit, allow less erasures. Okay, 0.44, nothing happens. 0.43, nothing happens. Now, if we have an epsilon of 0.4292, we see that the erasure probability steadily decreases until it eventually reaches 0. And we see that we are able to successfully decode our code in this case. And of course, if we decrease epsilon further, we require less iterations to recover from our channel. So to summarize, we see that there is a turning point, which is the threshold epsilon. And we can say that this is our epsilon star. This is the largest epsilon for which decoding is possible. So epsilon star was the largest epsilon for which decoding is possible. So we can do this, and we can calculate these thresholds epsilon star for different type of code configurations. We saw that for dv equals 3, we had 0.4292 roughly. And this is actually also the best configuration, dv equals 3. And if we change different variable knot degrees, we observe that we get a different performance. Okay, so dv equals 3 is the best, but we see that there is still a considerable gap towards the capacity. So we cannot achieve or get close to the capacity with this type of codes. So this is a little bit unfortunate. So how can we get closer to capacity? Well, there have been, since introduction of LDPC codes, there have been multiple attempts to get towards capacity. First attempt was something called irregular LDPC codes, which can close this gap, but these codes have an increased error flow, and they are not really suitable for high reliability applications. The second remedy is something called protograph LDPC codes, which is a generalization. And there we can optimize codes, but still having low error flows is quite difficult. So we need a new approach, and we choose one that extends protograph LDPC codes, which is called spatially coupled LDPC codes, which is a very special extension of protograph LDPC codes. So let's look at how spatial coupling works. So in the block codes that we have looked at, we always take a group of k input bits and then code it into a code word X. So we have block processing where the different blocks are independent of each other. What we now do is we allow a dependency between the neighboring blocks by superimposing a convolutional structure. so that the neighboring blocks can help each other during the decoding. One block may decode well, the neighboring not so. So this one block should help its neighbor. That's the idea of spatial coupling. So what we do is we introduce a new dimension, and it's called a spatial dimension T, to describe the different blocks. So inside the block, we have our usual dimension, and when we have another dimension to describe the blocks. And we introduce a new parameter, which we call the coupling width W. Okay, so let's take a look how this could work. So what we do is we first take our code and we use the graphical representation of our code. And we put 3 copies of the code along the spatial dimension. So we have a copy at spatial position t equals 1, copy at spatial position t equals 2, and a copy of spatial position t equals 3. So far, there is no coupling yet. Okay, so now the coupling works in the following way. We look at each edge of this graph at spatial position t, and then we do a random experiment. We essentially toss a coin, and then we check, depending on the outcome of our random experiment, we check if we should connect it to a spatial position t, t plus 1, or t plus w minus 1. And we do this with uniform probability. So with probability 1 over w, and we do it such that this degree distribution is preserved. So each variable node has 2 connections or dv connections. Each check node has dc connections. We need to be a little bit careful at the boundaries. So at the boundary, we introduce virtual positions such that we are able to fulfill the degree distributions. So let's take a look at how this works. So we have our 3 spatial positions, and we insert virtual positions at the boundaries. So now what we do is we remove all the edges of our codes. So we remove all these edges here, and then we start coupling. So we take each edge and we make a random experiment if we should connect it to this spatial position or one of the next spatial positions. And here we chase w equals 2, which means we always connect it just to the spatial position itself or to the next neighbor. So let's take a look. We do this for the first spatial position. So we actually did a random experiment, and we see this is the outcome. So we connect each variable node to a check node at T1 or the check node at T2. We see that all the variable nodes have 2 outgoing connections as we required it, but these check nodes or constraint nodes, they don't have. So we need to add new edges to the virtual position such that these conditions are fulfilled. So we do them, and we indicate the edges to the virtual position in gray because they are special and we need to treat them in a special way soon after. And now we repeat this process for spatial position t equals 2. So we do the same for t equals 2. Again, we do a random experiment, and we do it such that the degrees of the different nodes, they are fulfilled. And we do the same for the third position. So now we have connected all our 3 codes. The next thing we do is we remove the unused nodes. So these nodes, they have no connections. So we just remove them. Same for these nodes. And also these nodes that are connected to this virtual position, we can remove them. We can say that we fix these bits to be equal to 0. And then we don't need to transmit them. So these virtual positions are assumed to be 0. We don't need to transmit them. And this means we can remove them. And yeah, that's it. So the resulting code looks like this. So what we did is we took a code that had initially 6 bits, and we generated a new code that has 3 times 6, 18 bits. So there was a typo on my slide. So we have 18 code bits now. What happened is that due to the coupling, we generated 2 extra check nodes. These extra parity check equations that we have, so these are 2 extra constraints, they essentially decrease the rate of the code. So we suffer from a certain rate loss. That's what happens because of these extra parity check equations. So we can formalize this. So we started with this DVDC LDPC code, and we generated a new code that we indicate by a 4-tuple DVDC W and L. W denotes the coupling width, and L is the replication factor. So how many of those spatial positions do we have? So what we can note is that the check nodes, they have regular degree only at the inner spatial positions. At the outermost positions, they have a slightly lower degree because we have these connections to the virtual positions that we have removed. And we have extra check nodes, which also have a lower degree, and they will induce a rate loss. So we can actually calculate the rate loss. This has been done quite immediately after their introduction. And we see that the rate loss of the spatially coupled code, or the rate of the spatially coupled code, is essentially the rate of the original LDPC code. That's the regular LDPC code that we started, minus some expression. That depends on the coupling width of the parameters of the code, but also on the replication factor. Now we see that if we choose this replication factor sufficiently large, this whole term vanishes and the rate converges to the rate of the LDPC code. So proving this theorem is essentially a counting exercise. It's not hard. You just count the average number of variable and check nodes, and then you get the rate from these two expressions. So we omit the proving this, but you can look it up in the reference that are shown on the bottom of the slide, and I will also distribute the slides for your convenience. So how do these codes perform? Well, we do the same exercise and we track the asymptotic performance of our message passing decoder. And we do this using a very similar technique as we did for LDPC codes. Again, for the binary erasure channel, what we do need to do now is we need to track L different erasure probabilities, because each of those spatial positions must be treated slightly differently. So we have a CL at spatial position T, and we do this for every spatial position. At the boundaries, we fix our erasure probability to 0 because we don't transmit the virtual positions. And then we get a similar update equation that is shown on the slide here. So we first have a boundary condition, which means that on our spatial position, we start with erasure probability 1. We know nothing about the bits that we actually are interested in. And at the virtual position, we fix those to 0, so nothing is erased. Then we get an update equation where essentially we just need to average over the different x's from the neighboring spatial positions. So there is kind of like a filtering or smoothing that happens. And this filtering or smoothing is happens with uniform probability 1 over W. And that's what you see here in this summation. So this is just the smoothing or filtering effect. And now, again, if all these x's converge to 0, we declare success, can decode and abort. Okay, let's take a look at an example. Again, we choose the parameters as we did for the LDPC code. So we choose dv equals 3 and dc equals 6. And we knew that the threshold epsilon star for this 3.6 LDPC code was 0.4292. Okay, now we are very brave, and we immediately start to put epsilon equals 0.48. So let's see what happens. Now we look at the result after the first iteration, and here we plot the CL for the different spatial positions, and we take 100 of those spatial positions. What we see is that due to the boundary conditions, at the boundary, the erasure probability is slightly smaller. And this is because of the boundary condition, we know a little bit about the virtual position. So we fix these virtual positions. So we have a slightly better erasure probability at those virtual positions. So let's take a look at what happens if we start iterating. So after 2 iterations, 10 iterations, 20 iterations, 30 iterations, we see that at the boundaries, we get better and better and better. So we improve from the boundary, and we see that slowly carrying on during the iterations will converge to a situation where we have recovered all the spatial positions. So all spatial positions are actually becoming equal to 0. This is very good, so we can decode at an erasure probability of 0.48, which is significantly larger than what we could before. So let's be a little bit more brave. Let's go to 0.49. And what happens now is that we can increase the number of iteration, but nothing happens. So 200, 300, 500, nothing happens. So here we get stuck. There is no way that we can decrease further. Okay, so let's see. Why is this? So again, this summarizes. We have a threshold, essentially defined to be the largest epsilon where all these CL go to 0. And we see that spatial coupling could dramatically improve this threshold. So what is the key? The key is essentially the boundary effects. If we look at the boundary of our code, and especially if we look at the check nodes at the boundaries, constraint nodes, they have a lower degree. And essentially, this is a single parity check code. And if the single parity check code is smaller, it has better error correction capabilities. So we have better error correction capabilities at the boundaries. And these error correction probabilities help us recover the bits at the boundaries. Once we know the bits at the boundaries, we can propagate this information to the next spatial position, and it helps us recover the bits at the next spatial position. So we can slowly recover from the different erasures from the boundaries towards the middle of the code. And this is actually what happens in spatially coupled LDPC codes. So here's a toy example of why this works. So let's assume we want to push a wall over to the side. And we have a child. The child is just has the capabilities of its lungs, so it can blow the wall. And for some tiny walls, the child may be successful. But if we increase the width of the wall, the child is not going to be successful anymore in blowing this wall over. Then we can have a powerful device like a ventilator. And the powerful device can also push over some intermediate size walls, but it cannot push over big walls. So you can see the wall as kind of the LDPC code. And the width of the wall corresponds to the erasure probability epsilon. So small epsilon we can easily throw over, large epsilon, that's going to be more hard. The child is the message passing decoder, and our ventilation device is the maximum likelihood, so the optimal decoder. That's the best we can do. So at some point in time at the threshold, the child is not successful to push over the wall anymore, but a more powerful device like a maximum likelihood decoder would be. So how can we get from this threshold towards the maximum likelihood decoding performance? Well, we do something that is similar as in dominoes. So if you have a big stone that you want to throw over, you can start with small stones and you can slowly increase the width. So the child may be successful to blow over the very tiny wall. This tiny wall has enough force to push over a slightly larger wall. This slightly larger wall has enough force to push over the next wall, and until all the walls are being pushed down. So that's the idea. And we can do this. However, we have a cost of extra bricks. We need 3 extra bricks. So we can keep on doing this. And if we have more and more bricks that we want to push over, the extra cost of the bricks becomes negligible with 1 over L, or 3 over L in this case. So there is an analogy to the LDPC code, and each wall segment corresponds to 1 LDPC code. And the domino effect is the coupling of those LDPC codes. So we have coupled LDPC codes that correspond to these dominoes. And at the boundaries, we have our orange nodes that have a slightly less degree. And these correspond to our thinner walls that we put at the boundary. And the extra nodes, they correspond to the rate loss that we have. So this is the kind of analogy that hopefully makes it more clear why these type of codes actually work. And the belief propagation decoder will make them work. Okay, so here's a big table. I won't go into it, but we can see that the thresholds that we get, they're actually very close to the capacity of the erasure channel, which is 0.5. So we can actually calculate the thresholds, and we get very close to the capacity of the binary erasure channel. So if we take a closer look, and it has actually been shown that when these parameters of the code W and L go to infinity, actually this erasure, this threshold of the spatially coupled codes converges to the maximum likelihood performance of the underlying LDPC code, which is pretty nice. So we can achieve maximum likelihood performance with a very simple decoder. So what we can do is we can take a simple code where we know it has good maximum likelihood performance, apply spatial coupling, and then we get pretty good performance that approaches the maximum likelihood decoding performance. And this is shown in this graph. So with the regular LDPC codes, we could achieve this performance, this threshold, and with spatial coupling, we achieve the maximum likelihood threshold, which converges towards the capacity if we increase the variable node degree. So that's pretty nice. So we could see the problem is solved. Well, if you want to go to practice, there are still quite a lot of issues that you need to cover. So how can we practically implement these codes? Well, the first thing is that we look at how the decoding behaves. So here we have the performance of the decoding. So this is Xi after some iterations. So there is X here, so it's a different letter, but it's the same. And we see that the performance decreases from the boundaries, or the erasure probability decreases from the boundaries towards the middle of the code. And what we do here is we don't need to decode these positions that have already been decoded. There's no need for decoding those positions anymore. So even we don't need to run a decoder here. We also see that here in the middle, nothing happens when we are decoding. So there is no need for doing actually some decoding steps. So what we do in the practice is we use a window decoder. So we use a window decoder, and that's this decoding window that we slide over the code, and that actually follows this kind of wave through the code. So we do this, and we see that we just need to we'll just carry out operations inside this green part, and that's actually sufficient for decoding. So that leads to a very simple decoder and very low decoding complexity. And actually, the decoding complexity is linked to something called the decoding velocity of the curve. So decoding velocity is actually the velocity, how fast this curve is going to be displaced from one to the next position. So it's the number of iterations that we require for going from this curve to this curve. And actually 1 over this number of iterations. And that's the decoding velocity. It means if this velocity is faster, then we require less iterations for carrying out the decoding. So we have another parameter of how to optimize for the complexity of decoding. Okay, so let's take a look. So we have this window decoding, and this window decoder, the complex of this window decoder is actually directly linked to this decoding velocity. And we have a bunch of papers on the decoding velocity, and I will not go into the details, but you can look those up later if you are interested. So for window decoding, you can just take your favorite decoding algorithm and only operate on parts of the decoding graph. And then you shift your positions. So you can do this. And actually, we tried to implement this. And we had that was when I was working in Bell Labs, we were looking for coding for optical communications, where we have very high throughput and we need very low error rates. So we require error rates that are in the range of 10 to the power minus 15, so 1 bit error per 10 to the power 50 bits. And this corresponds to 10 bit errors per day if you transmit with 100 gigabits per second. And in order to do this, we actually built an FPGA-based decoder that can run the decoding at pretty high throughputs so that you can actually evaluate in Monte Carlo simulations these very low error rates. And we actually see that the error rates behave quite nicely. And we could get a gain of 0.4 dB compared to a conventional LDPC code at a bit error rate of 10 to the power minus 15. And this is a code that has been implemented on a chip that runs with fixed comma operations, that has a strong quantization, that has limited number of operations that you can actually perform. And we are within 1 dB of the capacity. So the asymptotic limit is 2.6 dB, and we are less than 3 dB. So we are at 1 dB from capacity with a very practical decoder that could be implemented in the field every time. So 0.4 dB is not too much, but actually it's quite a lot if you think of optical communications. So just as a number, 0.4 dB could lead to an increase of 900 kilometer of the reach that you can use in trans-Pacific fiber optic cable, so that connect the US with Southeast Asia. And that's quite significant. So it probably prevents you from adding extra regenerators, and it will allow you to get more system margins. So that was a pretty nice result, but we wanted more. So as a researcher, you're never satisfied with what you have, so you always want more gains. Okay, before we get to how to get more gains, this is an overview of quite a bunch of different codes that have been proposed for optical communications. The rates of the code, they are usually between 0.95 and 0.8. The code that I've shown you on the previous slide was this guy. So this is actually the code that we have designed that was on the previous slide. And we are 1 dB, less than 1 dB away from the theoretical optimum. And there are some bunch of other codes, both for soft decision decoding and for hard decision decoding. And this is something we compared from all the information that was publicly available. And you can get a full table with the numbers in a book chapter that we have just recently released. So you may look this one up if you're interested in the different practical aspects of these coding schemes. And when we take a closer look, we see that there are actually a bunch of spatially coupled codes that are already being implemented, and they are all among the most well-performing codes, both in terms of soft decision decoding and in terms of hard decision decoding. So how can we improve these codes? Well, one possible improvement is something called non-uniform coupling. So we saw that when we're looking at the thresholds that we computed, there was still a gap to capacity. So how can we close this gap? Well, if there is a gap and our construction is limited, we should always need to find ways to generalize our construction. Generalization always gives us more possibilities in getting gains that we probably didn't have before. So how can we get this generalization? One thing we looked at was non-uniform coupling. What we did now is take each edge and connect it with probability 1 over W to one of the W neighboring spatial positions. So we give up this, this constraint on how we couple and allow for non-uniform coupling. So now we allow that each edge connects to position Z with probability alpha and to position Z plus 1 with probability 1 minus alpha. So we just allow between two neighboring spatial positions alpha and 1 minus alpha. Okay, so then we can also write an update equation. Now this filtering that we have in the update equation is not weighted by 1 over W, but by a weighting vector nu. And this is the weighting vector, and this is just alpha and 1 minus alpha if W is equal to 2. We can also calculate the rate. And interestingly, we can also improve the rate loss. So for W equals 2, the rate loss becomes maximal if we do the uniform coupling. If we do the non-uniform coupling, we can actually improve on our rate. So let's take a look at an example and how this could improve the performance. So here's the density evolution for epsilon equals 0.48 of the conventional code with uniform coupling and the new code with non-uniform coupling. What we saw is that this conventional code has this two-sided convergence. So we converge from two sides and go towards the middle. In practical systems, we use this window decoder. So we actually don't need this two-sided convergence. We just need to track this one part of the code, and then we follow it throughout. And we give up this two-sided convergence and look at the single-sided convergence. So this is the non-uniform coupling. Alpha has been optimized to 0.35, and we can see that we are actually faster. And we even require less iterations for full convergence. So after 1,700 iterations, we have already converged with the non-uniform coupled code, but not with the conventional one. And the wave this one-sided decoder needs to follow is significantly faster than the one in the conventional scheme. We can optimize this parameters alpha, and depending on the parameters of the code, we can see that we actually get very close towards the capacity. So on the right-hand side, this is uniform coupling, and we see that with uniform coupling, we only have a few parameters of the code where we actually have good thresholds for W equals 2. No coupling gives bad performance, as we have seen. But if we do non-uniform coupling, actually we get somehow independent from the parameters and get closer to the capacity. We can generalize this to non-uniform coupling with W equals 2. Optimizing the coupling vectors becomes more difficult. We use a tool called differential evolution, and we have published the details last year at the ITW. If you want, you can look it up there. And what we do is actually we optimize for this decoding speed or this decoding velocity. And what we saw is that at a certain binary erasure channel, we can always have the highest decoding velocity, and we can be significantly larger than the decoding velocities of the conventional codes. So these are the decoding velocities of the conventional codes, and the green curve is the one that we optimized. And depending on the coupling width, you can actually even have larger decoding velocities. So the bigger you couple, the larger your velocity becomes. So that was actually quite nice result. And we also had simulation results showing that for a constrained complexity, you can actually improve the performance quite a bit. So in the next part of the presentation, I will look at the burst correction capabilities of spatially coupled LDPC codes. First, give a little bit of the theory, and then only later show an application example, which actually motivated this investigation. So spatially coupled LDPC codes. They have quite a lot of unique properties, and we'll just look at one scenario right now. So we assume that all the spatial positions have been correctly received, except one spatial position, which was completely erased. This could be, for instance, a packet loss in a data network, could be a server failure in distributed storage, or it could be impulse noise in like DSL systems. So now we can ask the question, when can we recover from this burst? And there's actually a very beautiful result that actually we can recover from the burst if this coupling factor W is larger than epsilon star to power of -1, 1 over epsilon star. And epsilon star is the threshold of the underlying LDPC code. So we start with an LDPC code, which has a threshold of epsilon star, and we perform coupling. Now, if we erase one spatial position, then a necessary condition for recovering from the spatial position is that W is larger than 1 over this threshold. This is quite a remarkable, very simple result. So let's take a look. Then, of course, we simulated this, and we constructed codes with a different number of bits per spatial position. So M is the number of bits that we use per spatial position now. So sorry for using M twice, but M is usually used twice in these contexts. So we look at different W equals 3, W equals 4, and we find that we actually should be able to recover from the burst. Our necessary condition is fulfilled, but it's only a necessary condition. And we see that we get quite large error rates on the range of 10 to the power -3. So what happened? And what happened is that the decoder cannot recover from this situation because something happened that is called size 2 or stopping set. So what happened is we have two variable nodes, and they are connected to check nodes in the following way. So we have this situation, and if these two are erased, it means that these parity check equations, we can never infer what the values of these parity check equations could have been, because we have two erased inputs, and these both could be equal to 0. Then we would fulfill it. Both could be equal to 1. Then we would also fulfill the parity equations. So we cannot recover from this situation. So we have some finite length effects due to the construction. We cannot recover the bursts. And but nice thing about this is that there's actually a combinatorial analysis that we can carry out. And the details again are in our paper from 2 years ago. And there we have the full analysis. So I'll just show what's going on. So we can actually count the probability that this situation happens. This is a purely combinatoric argument, and it's just a counting exercise. And you get a probability that two such nodes form such a stopping set, which we call PR. I will not go into the detail. The detail is not necessary. What we can see here is that if the number of nodes per spatial position grows, this probability will decrease, which is what we have observed already. And then we use something to bound this, to bound the error probability. What we use is the second moment method, which is essentially Cauchy-Schwarz inequality, which gives us the probability that x is larger than 0, allows us to bound this one, and we use it as a probability that such an event happens, or at least one of those events happens. This gives us an error probability. And then we also need to bound the joint expectation, and we have expression for these. Again, it's a combinatorial exercise. And we actually get a lower bound on the error probability. So you get an error probability that's lower bounded by this rather simple expression. We have this probability that we have computed 2 slides ago times some simple binomial coefficient. And we can actually compare this with our simulation, and our lower bound matches the simulation quite perfectly. So it's quite a good bound, and it allows us to estimate what's going on. Now, this is actually quite good because now we have a tool, we have an equation that we can use to actually assess the performance and actually optimize also the construction. So what we can do is we can look at how to get better error rates. And what we can do is we can expurgate the code. So if this situation happens that causes a high error rate, it means that we should expurgate the code. So remove those structures during the construction. And this is actually equal to increasing the girth of the graph, so to say. So if you look at the graph argument, and we can actually calculate probabilities that this happens then also in the expurgated case. And we see that if we actually do this expurgation and if we optimize our parameters, we can have error probabilities that are in the range of less than 10 to the power minus 15. So very low error probabilities with quite little effort. So that's very nice. And then we can start to slowly more generalize this analysis. So we look at the case where we not only have erasures in this one spatial position, but also in the neighboring spatial positions. We can get expressions for that one. I will not bother you with the expressions here. You can all find these in the paper. And again, we match our simulations quite well. So we can use these also for optimizing the parameters of the code. And we can also look at when the whole situation will not work anymore. So at what channel probability will have so many erasures that will not be able to recover from them. Then we can look at what happens if there is a burst that happens at a random position. And we can actually carry out density evolution. Again, I will skip over these. So we can look at burst that happens at a random starting position. And then what is the largest burst error that we can correct in a guaranteed way. So it's the smallest beta, smallest burst that can happen at a certain position. And we can determine this beta max also using density evolution methods. And we find that if the burst happens not exactly at the boundaries, but if it spans actually more than one spatial position, then we can correct longer bursts. And we can again extend our theory to this case to get arguments on the error probabilities. And this is what we get. So here we have situation, the error probability of the decoder. We can correct up to a burst of length beta max, which in this case is 1.6 times the length of a spatial position. So more than 1.5 spatial positions for any random starting position. And we simulate normalized bursts, and we see that we have error probabilities, lower bounds on the error probabilities. And we see that they, together with this beta max, allow us to describe the situation quite nicely. So if m, the number of variable nodes per spatial position, increases, we'll actually converge to both beta max curve and the lower bound on the error probability. Okay, so now we can do this also for a different configuration. So if we had w equals 3 before, if we increase w equals to 4, it means we can correct for longer bursts. In this case, it's more than 2 continuous spatial positions can be completely erased, and we can still recover from the erasure event or from the failure event. So this is actually quite nice code for something called distributed storage. So how did we get to looking at the burst erasures? Well, we had one application example that I will not like to go over because it shows that these things are actually connected to reality. And it also shows that many practical problems that you have, they are very well nicely connected to an underlying analysis. And it always makes sense to connect these two, because I believe that there is nothing more practical than a good theory. So what was this example? It was an example that was motivated by multiple access scheme. So burst erasures, they come in different varieties, like random access schemes, for instance, slotted Aloha when you have collisions. They also come in strong block fading channels, due to impulse noise, or in server failures in distributed storage. So we looked at actually a network, and we looked at something called the metro network, which connects different buildings on a campus or different mobile access networks. And we have a fiber-based network. And in each of those hops in the middle of the network, we have switches. And the way these switches work is that they have implemented the full physical layer. So in each of those switches, we actually carry out receiver signal processing, demodulation, channel decoding, and then you make a decision. If you should drop the traffic or if you should add new traffic, you make a switching decision. And then you re-encode everything and go to your line again. But this encoding and decoding takes a lot of effort. So the energy, you want to improve the energy efficiency. So how can you do this? Well, you can do this by not carrying out the decoding all the time. So what we did is we said, okay, we're going to do the switching on the noisy data and only decode the little bit that is actually meant to be decoded. So for instance, if you have a mobile cell tower that's attached, it's usually attached with 10 gigabits per second, but the traffic on the main line is 400 gigabits per second. So you need to decode 400 gigabits per second, remove 10 gigabits per second from this chunk, and then re-encode the 390 remaining megabits per second again. So we decided, let's keep everything in here encoded, and just decode when we want to decode. So just decode here, so to save the complexity. And we have a header, and the header, which is strongly protected, allows us to do the switching decisions. So it's kind of like a decision and forward relay that we do here. And what we do is we do a decoding, a container-based transmission of our code words, and we add the data to empty parts of the code word. So that's shown here. So we have a data container that contains a certain amount of data. So we are on one of those switches. We are at this position. And the rest of the container is 0. So now we want to add data to the container. What we do here is we put the new data into the empty part of the code word. We generate parity bits, and we exploit the fact that we have a linear code. So we generate a new code word that contains the 2 data portions and the new parity information. So that's the usual way it worked. And the idea is, if we take a look at this, and if we take a look at the very simple situation where we have a source, an intermediate node, and a destination node. So the source has few parts of the code word that are filled, and now it goes to the intermediate node. We don't do decoding, but the intermediate node adds new data. So it takes new data, it adds them in the empty positions, and we travel to the destination node. So now the data that has traveled from the source to the destination, the green data, it's much more erroneous than the blue data, because the blue data only needed to be transmitted over the second hop. So the blue data is much better than the green data. So what we do is we model the green data, because it traveled a big distance, as burst errors. And we can use our theory to design codes for this. And we actually do this, and we can get quite big improvements. So what we see here is the pairs of distance that we can cover. So we can cover the distance of hop 1, so from source to intermediate node. This is the distance of hop 2 from intermediate node to the destination. And we compare the naive approach in blue and the spatially coupled code. Now, if the amount of data that we transmit from the source to the intermediate node is not too large, then we have short bursts. And then with our optimized codes, we can actually get quite a significant improvement of coverable distances. So if the source data is only 1/4 of the data that we add at this intermediate node, then we can double the conveyable distance using our optimized burst-able correctable code. So that's quite a big improvement. Okay, with this, I'm already at the end of my lecture. I hope you enjoyed it. And to conclude, spatially coupled codes are a very powerful class of codes that extend LDPC codes. We can get record coding gains in optical communications. It's a very good approach to design parameters that are still unknown. So we still don't know how to fully design these codes. So we have quite a lot of open research problems still. And the general concept of spatial coupling also applies to other scenarios and to other areas of science like compressed sensing, statistical physics, etc. And we have quite a lot of applications in distributed storage, random access, fading channels, subscriber lines, etc. So it's quite an active area of research. Thanks a lot for listening. And with this, I am closing my talk, and I hope you enjoyed the school. And I'm very much looking forward for your questions. Thanks a lot. Goodbye.